Hello and welcome. I hope you are having a great day. In this video, we are going to start probability. So let's begin. Let me share my screen. I hope the screen is visible. So before beginning, let me set up the agenda. So in this video, we are going to cover the below topics. So agenda would be, first thing is, why do we need to study probability? What is probability? So that would be what is probability. So first of all, let's define the term, understand why is it required. Okay, second thing is sample space. Third topic is what are discrete and continuous variables. Okay, we'll discuss that. Then we will talk about what are mutually exclusive events and independent events, mutually exclusive and independent. Then we will discuss about conditional probability, very important. This is the base. An extension of this is Bayes theorem. It's very important, very much used in machine learning. We have an algorithm called naive Bayes. Okay, so that is there, and we'll dive a bit deeper into independent events. Okay, sorry, and we'll discuss about independence of events. What are the kinds? Independence of events. So there are three kinds of independence. So first is mutual, then we have pairwise, and the third one is conditional. This is very important. So generally these two, mutual and conditional, these two are very important to know. These are used widely. Pairwise not so much in machine learning, but for the sake of completeness, I'll be covering this too. Okay, so this is the agenda for this video. Okay, now let's start one by one. So first, let's build up our intuition. Why do we need to study probability in general? Okay, so the world around us is very uncertain. Okay, everything around us, we don't know what will happen exactly, and probability gives you the measure of this uncertainty. How do we measure this uncertainty? Whether something will happen or not happen, whether it's impossible or whether it's certain, and everything in between. Probability is the language that captures this uncertainty. Okay, so let me define what is probability. So first of all, probability, what is this? So this is the base, and from here we start. So probability, if we say, it's the numerical measure. So I'll keep on defining the terms also for your benefit. So this is a numerical measure. Okay, it's the measurement of likelihood or chances or chance of a particular event to occur. So this is probability in general. For example, tossing a coin. When we toss a coin, we get heads or tails. So we toss a coin, we get head or tail, and the probability for each one of them is, say for example, if we say probability of head, what is the probability of head when we toss a coin? It's a fair coin, so it's 0.5. Similarly for tails. Okay, and then we roll a die, we get numbers in the range of 1 to 6. Okay, that is there. Similarly, we will define the other terms. So before going into the other term, that is event, so the range of values that probability takes is, the range is from 0 to 1 and everything in between. So in general, what you have studied till now, you say that if the probability is equal to 0, you say that something is impossible. And if you say if the probability is equal to 1. So you say that this is certain or sure. So we'll discuss about this understanding also. This is not the exact definition. We cannot say probability is 0 means that event will not happen. That's impossible. If it is 1, then it's certain and surely it will happen. Okay. So generally in probability terms we say that it is, if probability is 0, it means that it is highly unlikely. We don't say that it's impossible. It's highly unlikely. Okay. And when the probability is 1, we don't say it's certain or sure. We say that it is almost sure or almost certain. So that's the definition. I'll discuss about these two terms in more detail, why it is so, and I'll explain this to you with the help of an example that is very easy to understand. So we use this term also, that is in the common terms. Also in certain cases we say this is the definition, but this is the more general definition that we should stick with. This should be our understanding of probability. Okay, so let's begin. So let me define some terms before I proceed, so that it's easier to understand. So before when I mentioned you, right? So this is the thing I mentioned to you, that particular event. So what is an event? Okay, what is an event? So anything. So you do any experiment like tossing a coin. Okay, when you toss a coin, that's an experiment. Okay, I'm doing an experiment. Let me see what will happen. Whether it will be a head or a tail. Okay, I don't know. So you do an experiment. You try to find out what is going to happen. You roll a die. Okay, a fair die, and you can get anything in the range. Okay, anything in the range of 1, 2, 3, 4, 5, 6. You don't know what's going to come. So that's an experiment, and you can get anything in this range, any number in this range. Okay, and when, okay, so this is the range. And for example, if I say that I want to find out, okay, that this is my event, that my event is that whether 5 will come or not, and I want to find the probability of that. So my event is occurrence of 5. I want 5 to happen, and then I'll measure its probability. So let me define the event for you. So event means, so when I say event means an outcome or a set of possible outcomes of an experiment, as I mentioned here, right? This is an outcome or a set of possible outcomes of an experiment, like rolling a die. Okay, these are my events, whether I can get a 1 or a 2 or a 3 or a 4 or a 5 or a 6. Okay, any one of them. Okay, so to define formally, an event is an outcome or a set of outcomes that is possible. Okay, outcomes of an experiment. If we toss a coin, we'll get either head or tail. So tossing a coin is head or tail. We get. So this is how we represent a set of events. Okay. So for example, okay, as I mentioned, if you toss a coin, you will get whether a head or a tail. Okay. So we have defined probability. We have defined what is an event. This is the base. Okay, the base. You understand what is a probability now. Before diving deeper into what is more into it, so as I mentioned earlier in the agenda, let's discuss about what is a sample space, and then we'll go in this order. Okay, so the next term that you should know is what is a sample space. Okay, instead of writing this, I'll just write sample space. So what is a sample space? So a sample space is nothing but, for example, if I roll a die, right? If I roll a die or toss a die. So what are the set of possible outcomes? What all we can get? Either can get a 1 or a 2 or a 3 or a 4 or a 5 or a 6. So these are the only possible outcomes that I can have, right? So this is my sample space. I can get only anything from this set of numbers only. I cannot get a 10 when I roll a die. This is outside my sample space. Okay, I cannot get a -1 when I roll a die. This is outside my sample space. So my sample space is only this. So this is my sample space. So if I want to define it formally for you, it contains all possible outcomes of an experiment. Outcomes of an experiment. So this is what is a sample space. So I can give you more examples. For example, if you have if you want to you have the number line and you want to choose any number between 1 and 2. So my sample space is this whole number line segment, the whole range. So what will be the number of what will be the range of this? How many numbers are possible between 1 and 2? How many real numbers are possible between 1 and 2? That will be infinite. This will be infinite, because we can have anything between, say for example, if I have 1.2, I can have 1.21, I can have 1.211, I can have 1.2111, and so on. So these numbers are infinite. Okay, so this is, I hope you understand what is sample space. Okay, these are all the possible outcomes when you say that. Okay, when you do an experiment. So my experiment is, like for example, in this case is, my experiment is to find any number between 1 and 2, and there can be infinite such numbers. Okay, so this sample space. Okay, so there is something more advanced stuff that I'll just mention here, and the lecture notes, what will have, the notes will have the details of that. So you should know that this sample space should follow something called, it should follow the rules of sigma algebra. It's just good to know stuff and some advanced stuff. Okay, so there are some rules that this sample space should follow, but I'll not dive deep into this. I'll write it in the notes and share it with you. Okay, so don't worry, but you should just know about this, that this sample space should follow the rules of sigma algebra. Just good to know stuff. Okay, so this is about sample space. Now let's move to the next topic. The next topic would be what is discrete and what is continuous. What is discrete and continuous? So what is discrete? For example, discrete is anything that is countable. For example, when I do toss a coin, there are only two possible outcomes, right? Head or tail. So this is discrete. If I roll a die, I can have only 1, 2, 3, 4, 5, 6. These are the only possible outcomes. So this is discrete. Okay. And then we have something called, okay. So for example, if I am sitting on a traffic light, okay, I'm sitting on a traffic light and measuring the number of cars, sitting on a traffic light and measuring the number of cars that are passing through that traffic light or crossing that traffic light in 1 hour. This is also finite and fixed number of events. So this event is also discrete because that's countable. Okay, so this is discrete. So let me rub this off for avoiding confusion. So this is only about discrete. These are discrete events. I hope that is clear. The next thing is continuous. So continuous is anything that is like a graph, anything. If you have like this, right? So this is a continuous graph. If you see, there is a continuity. So this is continuous. There can be infinitely many points between any, if you take any 2 points, right, there can be infinitely many points. This is continuous. Similarly, on a line segment, the previous example that I mentioned, if you have to choose any number between 1 and 2, okay, so there can be, in this range, there can be infinitely many numbers. As I mentioned earlier, there can be 1.2, 1.211, 1.2111, etc., etc. So there can be infinitely many numbers. But just understand one more thing here. Say for example, if you fix the places of decimal, to which we are counting. Say for example, if I say that if I will count only till 2 places of decimal, okay, then this becomes countable because we know how many numbers there are. This is countable. So then this becomes discrete if we fix the number of places after decimal, okay, in the range that I want the numbers to be. So this is my continuous. Okay, so it can take any value within a given range. So this is your discrete, this is continuous. Okay, also for example, if I give you one more example, say I have a rectangle, and if I want to put any point in this, there can be infinitely many such points that can be put in this region, right? So this is also a continuous variable, or a infinitely many possible points can be put in this. Okay, so to summarize this, so you have a sample space. So I have a sample space. So this can be divided into two parts. So it can be either finite or infinite. Okay, so if it's finite, then it's discrete. We know roll a die, you can get a finite number of events, finite number of possibilities. So that's discrete, no problem. But if it's infinite, then either it can be countable or uncountable. If it's countable, then we say that it's discrete, and this is the only case where it's continuous, when the possibilities are infinite. This is discrete, this is discrete. Anything that is countable, even if it's infinite, okay, say for example all the numbers on the number line, even if it's countable, we have like all the numbers on the number line 1 2 3 4 5 6 like this till infinity. So these are countable. So this is also discrete. Okay, discrete. Okay, so we have understood what is sample space, we have understood what is discrete and what is continuous. Now let's move to the next topic. What was our next topic? So this is done, this is done, this is done. Now let's move to mutually exclusive events, mutually exclusive and independent events. So let's go. So what do you mean by the literal meaning of mutually exclusive? Okay, so mutually exclusive also means disjoint. So if you see from the set perspective, right, set theory perspective, if there are two sets, say for example there is a set A and there is a set B, okay, A and this is B, there is no overlap. There is no overlap. Either it can be in this way, or it can be, the two sets can be like this. So this is the two possible. When these two sets A and B have no overlap, these are called disjoint or mutually exclusive. Okay, and when there is an overlap, these two sets A and B, these are not mutually exclusive because we have an overlap here, and this overlap is called A and B, and it is mentioned A intersection B. So this is a mutually exclusive case. So what happens? So what do we say? Okay, so let me define it for you. Mutually exclusive. Mutually exclusive means no overlap. Okay, this is also sometimes called disjoint. This is also called disjoint sets. These two sets are called disjoint. They are not joint anywhere. This is no overlap or any common outcomes. Or any common outcome. Okay, and there's one more thing that we can say for sure is, if we are choosing anything from here, if we are choosing anything from A, then we can say for sure that we are not choosing anything from B. That means in simple terms, if A happens, then B will not happen, that we can say for sure. So if we know that two events are mutually exclusive, means we can say that if one has happened, then the other will definitely not happen. So this is what mutual exclusion means. If one happens, then we know that the other has not happened. Okay, so let's understand from it from the perspective of set theory. We say, right, A union B is equal to A plus B minus A intersection B. How does this come? I hope you know that this is A plus B. So if you want to find what is there, either A union B means this is A or B. If I want to find anything that has happened in this, anything that is either in A or in B, then that is denoted as A union B or A or B. That is given by A plus B minus A, and this is read as A intersection B is read as A and B. That is the overlap part. Okay, so we know from for mutual exclusion, right, what will be this overlap part? This overlap part in mutual exclusion is nothing. There's no overlap. So this A intersection B will be 0 for mutual exclusion. A intersection B is equal to 0. There's no intersection or overlap. So we can say that A union B is equal to A plus B. And in terms of probability, we can say that, okay, we can say that probability of A union B is equal to probability of A plus probability of B for disjoint or mutually exclusive events. And in general, it is A union B is equal to probability of A plus probability of B minus probability of A intersection B. I have defined the terms for you. Probability of A or B happening and probability of A and B happening. This is A and this is B. Okay, this is quite simple. You can find out why it is there. Okay, if not, then we can create a video for that too. Okay, so this is defined. Okay, now let's move to what does independence mean. I hope mutually exclusive events are clear. It's very simple. There is no overlap between two events, and we know that if one has happened, then the other has definitely not happened. So what do we understand by independent event then? Independent events. Independent events. So what is the meaning of independent events now? Let me see. Let me define it for you. So outcome of one event, okay, does not impact the outcome of our other event. Okay, so let me repeat. The outcome of one event does not impact the outcome of other event. Here, so check the wordings. Here what we say, if one happens, then we know that the other has not happened. So that's the understanding. Things are very close, but understand the distinction. If A has happened, then we know that B has not happened. But in independent events, we know that if A has happened, then I don't know anything about B. Okay, so the outcome of one does not impact the outcome of other. That is independence. And here, if I know the outcome of one, then we know what is the outcome of the other. That is in mutual exclusion. If A has happened, then B will definitely not happen. But if the events are independent, then if A has happened, even then I don't know anything about B, what has happened, whether it has happened or not happened. That is independent events. For example, let me give an example. For example, if I toss a coin twice, so first time, okay, toss a coin twice. So first time if I get head, do I know, okay, that what will I get in the second toss? Does that impact the second toss in any way? No. All the events here are independent. Every toss is independent. So the first event that is the first toss, that is event A, is independent of the second toss and vice versa. Okay, if I toss the second same coin second time, I don't know what will happen. So these two events, the first toss and the second toss, are independent events. I hope that is clear. Let me write down the definition that I was mentioning. That outcome of one event does not impact the outcome of another event. Okay, so similarly, if I talk about this, what will be the, so here what will be this probability of A and B? The probability of A and B, this is given by, because both are independent, there's nothing, this is given probability of A into probability of B. Because these two are independent, nothing is happening, there's no relation between A and B, so there's no impact. Okay, I'll give you more information about this when we discuss about conditional probability next, and that will make it more clear. I'll revisit this, maybe I'll explain this again. Okay, but this is what is independent events. So I hope mutually exclusive events and independent events is clear. So to understand again, here mutually exclusive events, if I know one event has happened, then we know that other has not happened. So knowledge of one event tells me that, gives me some information about the other event. So that is mutually exclusive. But in independent events, the knowledge of one event, like tossing a coin, does not give me any information about the second toss. Okay, what will happen in second toss? So both the tosses are independent events. Okay, that is what. Okay, so let's continue. That is what is mutually exclusive and independent events. So now that we have understood what are discrete, what is discrete and continuous. Okay, we have understood this with an example. Let's revisit the thing that I was talking about earlier. What is the meaning of probability of 0 and probability of 1? As I mentioned, it's not always impossible. Probability of 0 doesn't mean impossible, and probability of 1 doesn't mean certain. Let me give an example so that you understand. So for example, let me continue with the same example that I was doing. So on the number line, I have 1 and 2. As we know from the earlier discussion, that there can be infinitely many points between 1 and 2. Okay, so now I ask you that what is the probability of getting 1.5? If I take my pen and put it on this number line, what is the probability of getting exactly 1.5? What would be the answer for this? That would be, probability of this will be almost equal to 0, because there are infinitely many points here. There can be anything, like for example, there can be 1.5, 1.51, 1.4911, 1.4999999999, 1.51111111, like that. There is no limit to this. So there can be infinitely many such points between 1 and 2, and there will be more numbers like this here. So what is the probability that out of these infinite points, that I put my point pen exactly on 1.5? So this will be almost equivalent to 0, because there are so many points. So that is why we say that it's okay. This is not impossible, but can you say that? Can we say that it's impossible to put my pen on this point? No, right? So that's why we say that there are infinitely many points. So probability of 0 means highly unlikely, not impossible. Because there is some chance that, because this 1.5 is there, so there is some chance that I can put it here. But for all practical purposes, we say that probability of putting my point on 1.5 is 0. I hope that is clear. So that is highly unlikely. Similarly, if I put the question in the reverse order, okay, so my question is, what is the probability of not putting my point on 1.5 exactly? What is the probability of not putting my point? I will choose, if I put my pen here, it should not fall on 1.5, anything apart from this. Okay, so can you say for sure? So what will be the probability? So since there are infinitely many points here, since there are infinitely many points here, so can we say that not choosing 1.5, what will be the probability of this? Exactly, what will be the probability? We can say that this will probability of not choosing 1.5 will be equal to 1 for all practical purposes, because there is almost, okay, we can say that it's because choosing 1.5 is so low that we can say that of not choosing 1.5 is 1. But can we say that for sure? Again, the other way around, that whatever I do, I'll not be able to use 1.5. We cannot say that surely, right? So that's why probability of 1 doesn't mean certain or sure. We say that this is almost sure or certain. It's not certain. In this continuous case. So this is the more accepted definition of probability of 0 or 1. Okay. But in practical terms, we discuss with mostly finite or discrete numbers. So from there, the definition that whatever we understand, right, p equal to 0 is impossible and p is equal to 1 is certain or sure. So this definition, what we know, comes from there. And I can give you a counter example also where this definition holds, and you guys will also know. Let me give you a quick example so that you understand. For example, when will this definition of probability p equal to 0 and p equal to 1 hold? Say for example, if I roll a die, I'll ask what is the probability of getting a 7? We can say that this is a 0, right? So that's why, and here in this case, we can say that it's impossible to get a 7. Here this definition holds, that getting a 7 is impossible because our set only contains 1, 2, 3, 4, 5 or 6. There, in this case, this definition will hold. Okay. And similarly, if I roll a die and if I say that what is the probability of getting any of these numbers, any of 1 or 2 or 3 or 4 or 5 or 6, in this case we can say that this is sure that I will get, and this is impossible. So in this case this definition holds, but for all practical purposes we use this, that probability of 1 is almost sure and probability of 0 is, where did it go? This is highly unlikely. I hope that is clear. Okay. Now let's move to the next point. The next thing is very important. So let's discuss about conditional probability. Conditional probability. So what is conditional probability? You must have heard a lot, okay, about this conditional probability. So if I define it, okay, so we say that likelihood of an event A Okay, what is conditional probability? So this is the likelihood of an event A occurring given that another event B has already happened. Okay, so let me define it and then I'll give you more. So likelihood of an event A happening given that another event B has already occurred, and the way we denote it is probability of A given B. So this is how we represent this slash is A given B. Okay, so this is the normal definition. So but in more in general terms, what we say is, so for example, we know the probability of A, that's we have some probability of A, and now something has happened and we have got new information, and based on this new information the probability of A should be updated. So we should use this new information to update the knowledge that we have already for probability of A. Okay, so based on that new information, update the probability. This is what is conditional probability. I'll write that also. This is the most, okay, this conditional probability allows us to update. This is the more important thing that you need to understand. Update the probability when additional information is known or revealed. I'll give you an example, you will understand that. For example, so I'll give you a definition. Okay, let me give you what does this mean. So let me cut it out from here. So this is given by probability of, so this is what is the definition. So this is let's say this is what is probability of A given B has already happened. This is probability of A and B. This is probability of B only. So let me not write this. Okay, this is probability of B. So let me give you an example so that you understand. For example, okay, I roll a die. Okay, so for example, I roll a die. Okay, and I'll define the two events. A is equal to, I get a 5, and B is equal to get an odd number. Get an odd number. So I have rolled a die. Okay, we two are playing. I have rolled a die, and you want to find out what is the probability of getting a 5. So before anything, any new information you have, so what will be the probability of 5? So the possible outcomes are 1, 2, 3, 4, 5, 6. These are the possible outcomes, and I want that 5 should happen. So out of 6, this is the 1. So the probability of A will be equal to 1 by 6. Now, so we both are playing. Okay, you roll the die, and I put my hand in middle, and I know the answer of what has come in here, what has come, but you have not known. But I reveal to you. Okay, so earlier remember that what is the probability? The probability of getting 5 is 1 by 6. Now, after you have rolled a die and you don't know what has come, but I have seen it, and I give you more information about it, that an event has occurred and that is an odd number. Okay, that is an odd number. So what would be this probability of getting either 1, 3 or 5? This will be half. So after revealing this new information, will the probability of getting A or getting 5 change once I have revealed you that you have got an odd number? Will this change? Yes, it will change. So let's write it down in the formula. So P of A given B. So A is getting a 5 and B is that I have given you new information has come that the number is odd. So what is the probability of both A and B happening? Let me draw it for you so that you understand. So generally these are not so easily understood. So for example, let's create this set world. So this is our whole sample space. This is given by omega. So the sample space is given. This is sample space. The symbol of sample space is omega. So this is all the possible outcomes. Okay. And in that I have okay. So this is my B, this is my A, and this is my sample space. Okay. So what are the numbers that can happen in B? 1, 3 is my 5, and outside this are all the even numbers 2, 4, 6. Okay. So what is now let's put it in the formula. This is what is there on your screen. Now what all things we need? P of A given B is equal to P of A and B, and so now since B has happened, so this is our only word. Earlier our sample space was this. Now we have got a new information in this whole sample space. Probability of getting 5 was 1 by 6. But after that a new information is revealed that the number is odd. Our sample space has decreased now because of this new information. Okay. And now if you can see here only from this diagram itself, what is the probability of getting 5 now? So all the possible numbers are 5, 1 and 3. These are 3 numbers. And out of that I want to get 5. So now the probability has increased to 1 by 3. And the same thing we'll understand using the formula. Okay. So we know intuitively that probability, updated probability P of A given B is equal to 1 by 3. You can see from here. But let it get it from the formula also. So this is what it defines. The probability of B means now the sample space has changed. So this is my world now. This is the only world. So anything that I want to calculate, I have to calculate within this world. So this is not my world now. This outside is not. So only this is the world. So probability of B. Probability of getting a B is, you know, probability of getting 135. This is half. Right? And earlier probability of getting A and B both from this formula. Understand, from intuition we understood this. Now from the formula, now what is the intersection of A and B? What is the common part? This is the common part. So this is, what is the probability of this? 1 by the complete thing, 6. So A and B is 1 by 6. So 1 by 6 by 1 by 2 will give you 1 by 3. And this is what we understood intuitively also. So this is what is our conditional probability. I hope this is understood now. Okay. Now let's move to the next topic. This topic is Bayes theorem. Very important. It's just a refactoring of conditional probability, but it's used widely. So this is Bayes theorem. So what does Bayes theorem say? So I'll just, this is just a formula, and then I'll show you something that is used. Okay. So we know that from the conditional probability formula, P of A given B is equal to P of A intersection B by probability of B. We can reshuffle this and we can say that P of A intersection B is equal to P of B into P of A given B, right? This is sometimes called as chain rule also. This is nothing but, you have seen, right? This is just a refactor. I just brought this here, multiplied these two, okay, to get this. So if this is there, so this is my first equation. second equation I can do the other way around too, right? The other way around would be just a minute. P of A intersection B or B intersection A, both is same, right? If we do it the other way around, this will become P of A into P of B given A. I hope we can write it this way also. You get it? This is my second equation. These two are same. A intersection B or B intersection A. Now let's refactor this. So now from this and we know that, so this is, sorry, I'll just write the equations as we do in our maths. So this is my first equation, this is my second equation, this is my third equation. So as we say, from 1, 2 and 3, what we can say? Let's rewrite. We want to write P of probability of A given B. Now how can we write A intersection B? A intersection B is same as B intersection A. These both are same. A and B or B and A, both are same, right? So I can replace this with this thing. Okay, so let me replace this. So this will be P of A into P of B given A. This is how we read it, and by P of B. This is what is called our Bayes rule, Bayes theorem. This is what is Bayes theorem, guys. Nothing but just a refactoring of this conditional probability formula. Okay, let's continue. I'll give you one more example of this. So there's something that you should know. Okay, I'll just find it and let you know. This will be useful when, just for your understanding, when we do it later. So just for your understanding, these are the terminologies, just to introduce the terminologies I will give you. So whatever I've written, so the terms that we, instead of A and B, I hope this is visible. So now replace A with hypothesis and B with A with H and E with evidence. Okay, so A and B. So probability of hypothesis given evidence. So this is your A, this is your B, and then this formula. So probability of hypothesis is true given the evidence. This is given by probability of hypothesis is true before any evidence is present. Okay, before any evidence we have, this is the probability that we had, like 1/6 in the earlier case. Okay, and then we have probability of evidence given the hypothesis is true. This is your given by probability of E given H. And then in the denominator we have probability of observing the evidence. So this is the terminologies that I wanted you to know, hypothesis and evidence. So this may seem like what is it, but this is nothing but the same thing, guys. Okay, so this is a Bayes theorem, and let me give you some more terms around this Bayes theorem. So this is just good to know. So again, probability of A given B is equal to probability of A into probability of B given A by probability of B. So what are these things called? So this is sometimes referred to as, just know the terms. This is called posterior, means after getting the new evidence or the new information what I have got, what is the truth now? Well, this is the posterior, and before, this is called prior. Before getting the evidence, so this is my probability of evidence, this is my evidence, and this is called the likelihood of that event happening. This is without anything, without any information. This was our earlier likelihood. Okay, and then this is the prior information, that what is the new information. Okay, what is the prior information that I got, and after this information, this is the posterior. So these are the terms that you should know and be comfortable with. So these are used very commonly in machine learning. Okay, So this is the thing. So I'll just give you one more example, the same example that we did, and we'll try to compute it, the same rolling a die example. Okay, so now we'll compute the same thing using Bayes theorem. So again, example would be, for example, we roll a die and my A is get a 5. So my sample space would be 1, 2. Now you should be comfortable. Sample space is denoted by omega, and A is get a 5. So P of getting a 5, this is I want, this will be 1 by 6, and the B would be same thing, get an odd number. So this will be probability of getting either 1, 3 or 5, and this will be half, because half of the numbers are odd numbers. So now if we want to calculate the same thing using Bayes theorem, how will we do? Probability of A getting given B. So this is probability of A into probability of B given A by probability of B. We'll compute the same thing, okay, using this. So we know, so this information we have, this is what we need. So let's focus on this one, probability of B given A. So let's read it, okay. What is probability of B given A? Probability of B given A is probability of getting an odd number given that I have seen a 5. Okay, given that we have got a 5. Probability of getting an odd number given that we have already got a 5. So what would be this probability, guys? Probability of getting an odd number, or that we have already seen a 5. So we have already seen an odd number, right? So what is the probability of getting an odd number now? So this probability will be equal to 1, because 5 is an odd number and we want to get an odd number. Okay, if we have got 2, 4 or 6, then this would be 0. But since we wanted to get an odd number and we know that we have got a 5, that is the information we have, probability of B given A. So we can say that this probability is 1, that I have got an odd number for sure. And if I plug this value into the formula, so probability of A getting a 5 given that I have got an odd number is probability of A is 1 by 6 into 1 by half. It boils down to the same formula, and this should be 1 by 3. Okay. Now let's dive deeper into Bayes theorem and understand its generalized form. Okay, let me give you what am I talking about. So we know that, so we have seen this example, we have understood Bayes theorem very well. Okay, so what is Bayes theorem? P of A given B is equal to probability of A into probability of B given A by probability of B. So now if you see this with the help of a diagram, so if you try to understand this, so we can draw this. See, this is our sample space, this is our A, this is our B. Okay, so we have A, we have B, this is our omega, our sample space. Okay, so now how can we denote B here? How can we understand B? So there are two parts. This is the one B, and then this is the rest of the B. So this we know, this is A intersection B. Okay, this is A intersection B. What can we say about this part? This, can we say that, or can we write it in terms of B? This is B intersection A. And can we say this is B intersection A complement? See, this is A, and intersection of B with this is B intersection A. And whatever is outside this, that is A complement. Okay, or A prime as we say. And intersection of B with that A complement, anything that is outside A, that is not A. Can we say that this is B of intersection of B with A complement? So can we rewrite B now? So can we say that B is equal to B intersection A plus B intersection A complement? Can we say that probability of B is equal to probability of B intersection A plus probability of B intersection A complement. Now let's put this in this equation. So what does our equation become now? Probability, the same Bayes theorem, this becomes probability of A given B is equal to probability of A into probability of B given A by probability of B intersection A plus probability of B intersection A complement. I hope this is clear. Okay, we have just replaced B with this. So now if you see, the sample space is divided into two parts. Let's extend this now further. So this is divided into two parts. One is A, other is A complement. So let me show you in the diagram. So if you say this is our sample space, okay, and it's divided into two parts. Say this is, one is A and another is A complement, and somewhere here in the middle our B is sitting. Okay, so this upper part is B intersection A and the lower part is B intersection A complement. So it's just a redraw of the same thing. So this is our A, this is our A, this is the whole sample space omega. This is our omega. So I'm just drawing it in circular way. And the remaining part that is outside A, the whole of this part, this is A complement. So can we say that our sample space is divided into two parts, A and A complement? And we are telling that, and we are giving the information about B as B intersection A, and this is B intersection A complement. So our omega is divided into two parts, and this is how we can give our B. Now let's take this thought a step further, and can this whole omega space can be divided into multiple such parts? Okay, what will happen then? And then we find out the intersection of B with that. Okay, so let's generalize it, and when we want to find the total probability of B, we are doing its complement with B intersection A and B intersection A complement. And now if you want to find the total probability of B with n such parts, okay, how will that be? So let me draw the diagram, and then let me reuse this diagram. Okay, let me redraw another one. So let's see, for example, if this is our sample space, so this is our omega, and let's say this is divided into n such parts. Okay, and somewhere in the middle there is our, so this is our B. And now instead of doing into two parts, dividing the sample space into two parts, A and A complement, I'm dividing into n such parts. Let me name them. So this is A1, A2, A3, this is still AN. So the sample space is divided into n parts. And now if you want to calculate the total probability of B, how will I compute that? How shall we do that? So can we write it that B is equal to B intersection A1 plus B intersection A2, so on till B intersection AN. These are the n parts, and my intersection of B with each of the parts. Okay, and finally if I sum them up, will give me the total probability of B. Okay, and this is called the law of total probability. Okay, this is called, whatever you have understood now, how to calculate the total probability of B, first using the two parts of A and A complement, and then generalizing it to n parts. This thing that we have understood, this has got a name, and it's called law of total probability. Let me write it down. Law of total probability. For computing any probability, we can use this law, and this holds. So let me define it for you. How is it defined? So I'll just write overall probability of any event B, what is given by considering all the mutually exclusive, okay, ways it can occur. Okay, so overall probability of any event B, considering all the mutually exclusive ways it can occur. Mutually exclusive means the part that is here, it does not overlap with this part, and whatever exists in this part. So all these parts are mutually exclusive. There's no overlap. So this is one part, this is one part, this is one part, and similarly there can be multiple within this. There are one parts. So all the parts of B are mutually exclusive. There is no overlap. So this is what mutually exclusive means. Okay, and what are the parts in this? So A1, and what is this? The A1, A2. What do we say about A1, A2, and AN? So these are the parts of the sample space, right? What do we say about this? A1, A2 till AN. Okay, our set of events. Our set of events that will make parts or partition the sample space. Okay, that will partition the sample space. What can we say about these parts also? These, whatever the parts of A1, A2, A3, these are there. These parts are also mutually exclusive, and sum of all these parts will form my sample space. So whatever is there, so these are the two rules. I'll just write it. So whatever you are seeing this in this diagram explicitly, I'll just write it in words. So these parts are mutually exclusive because there is no overlap between any of the parts, and sum of all these parts will form my sample space. So this is what we are going to write. So the first thing is about A1, A2, N, they are mutually exclusive. Okay, that is AI intersection AJ is equal to phi for all I not equal to j. So this is called null set, and this symbol is called for all. This is general. Okay, and this, you know, this is and what is the second part about AI to AN? Is we are talking about AI to AN, that they are exhaustive. Exhaustive means the whole. If we sum all the parts A1 to AN, they will form my sample space. How do we write it mathematically? A1 union A2 union dot 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 union AN is equal to my omega. This is my this is equal to omega. Omega is my sample space. Okay, this is what it is. This is my law of total probability, and using this, how will I write my B? Probability of B is given by sigma I equal to 1 to n probability of A of I into probability of B given AI. Okay, so how will it be? So this is summation. So if you break it down, this will be how will it be? What is this? Probability of AI into this given BI. This is probability of AI intersection B. This is what it is, right? How did we break this down? This is B intersection A intersection. So this can be written from the conditional probability, right? What is the conditional probability? Do you remember? P of A given B is equal to probability of A and B by probability of B. This implies chain rule. What was it? Probability of A intersection B is equal to probability of A given B into probability of B, right? So can this, in terms of probability, okay, can this be written as, now this whole terms, each term, just plug it in here. So what will it become? Probability of A1 given B into probability of B plus probability of A2 given B to probability of B, and so on, right? So that same thing is written here in the reverse order. I hope you get this point. So from the chain rule, we brought it down to this part. And now if you plug this thing in the Bayes theorem, okay, from where it came, from where we came. So now if you plug this in Bayes theorem, what will it get? What will we get if we can generalize it? So now we can generalize the Bayes theorem using this law of total probability. How will it be? Let me write it in different color. Sorry. Probability. Probability of AI given B. So probability of AI, ith. So I belongs to this 1, 2, 3, 4, n. Probability of AI given B is equal to what it will be? Probability of AI into probability of B given AI by summation j equal to 1 to n. I'll use another variable in the denominator. Okay, probability intersections part, we'll write it as chain rule. Probability of AJ into probability of B given AJ. So this is a generalized, this is generalized Bayes theorem. And this is our law of total probability. Okay, so with this, I hope this is clear. So we have just extended the theory. Okay, to summarize, we found out the probability of B as B intersection A and B intersection A complement. From dividing the whole omega into two parts, we move it to n parts, and from there we can get the total probability of B. That is called law of total probability, and we got this one here, this formula of B, that is the total probability of B, and then we can write it as in the form of conditional probability, because A given B, we know that from the chain rule, right? This is a chain rule. This is the chain rule. From there, we can write it in the mathematical formulation as this form, and the same form we'll plug it into the Bayes theorem and generalize it, and now we get this generalized Bayes theorem formula. Okay, so this is with respect to Bayes theorem. Okay, now let's move to the next topic. So what is our next topic? That is the last topic. Last topic is, so we are done till here. Okay, conditional probability done, this is done, and now we'll discuss about independence of events. Let's move. So the next topic is independence of events. So we have seen already independence of events, but we'll see the three parts. Okay, what are the types of independence of events? So what are the three parts? There are three kinds of independence of events. One is mutual independence. Second is pairwise independence. And the third is conditional independence. Okay, so let's go through that. Okay. So what was the meaning of independence of events? That occurrence of one event does not influence the occurrence of other event. Okay, so let me write it down. Independence means occurrence of one event does not influence the probability of occurrence of probability of the other event. Just I'll write in shorthand, probability of the other event. This is what in short independence means. Let's see the first one. The first one is mutual independence. So mutual independence, What is mutual independence? We know whatever we have learned already. So mutual independence means P of A intersection B is equal to P of A into P of B. Both are independent. Okay. This term is also called as sometimes joint probability. Okay. For example, toss a coin twice. We have seen this example during the independent events. Okay. If I toss a coin twice, so if the first toss, whatever is the outcome of the first toss, does not influence what will come in the second toss. For example, if I get a heads in the first toss, it doesn't influence what will come in the second toss. We don't know. So getting a head or tail is 50-50 again in the second toss also. So the first toss and second toss are independent. So this is your example of mutual independence. And this term of two events occurring together is sometimes called joint probability. Okay. Now, for example, as we have seen this, right? So we have seen this example already. This is independent. So now let's move to the second one. The second one is, this is a bit pairwise independence. So when we say independence means we mean mutual independence. Okay. So this is our mutual independence. P of A intersection B is P of A into P of B. Okay. Now pairwise independence. So let me give you an example and you will understand better with that example. So let's define our three events. We are doing again a coin toss experiment and three events let me define. So the first event is, okay, A is that I get a heads in, I get the same outcome in first and second toss. So the experiment is toss a coin 3 times. Okay, what is A? A is first and second toss are same. So example, if I get heads in first, I should get heads in second. If I get tails in first, I should get tails in second. So what will be our this thing? It will be HH or TT. Okay, this implies probability of A will be how much? So out of all the combinations, there will be, what will be our sample space here? The sample space will be head head, head tail, tail head, tail head, or tail tail, right? This is our sample space. So out of these 4, I get 2 out of 4. This is equal to half. Similarly, my B is getting, so I'm tossing a coin 3 times. So my B is getting same outcome in second and third toss are same. So again it will be same thing, and my P of B will be equal to half, and similarly C will be third and first toss. Okay, and my probability of C will be half. These are my individual probabilities A, B and C. Okay, this is the experiment and this is my events. So now let's check for pairwise independence. So pairwise independence means, say for example, if we see check A and B, what will be P A intersection B? A and B both happen. What does this mean? That I get the same outcome in first and second toss, and B means I get the same outcome in second and third. So from, if I want A and B both to happen, this means that I get the same outcome in both, all the 3 tosses, A, B and C. Means all the 3 times if I toss, I get the same outcome. This is what A intersection B will mean. So what it will be in words, that A is first and second is same. I hope you get the point. Okay, so P intersection will be sorry, probability of getting in all the 3 tosses head 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 or tail tail tail, right? A and B both are happening. Okay, so what it will be? What will be the value of this? All the 3 tosses are, all 3 tosses are same. I'll write it for you in words. This is what it means. So what will be the value of this? So probability of this will be 2 by 8. This is equal to 1 by 4. Because if you see, right, so there will be if I have one coin, there are 2 outcomes. If I have 2 coins, there are 4 outcomes. If I have 3 coins, there will be 8 outcomes, right? I hope this is 2 to the power 1, 2 to the power 2, and this is 2 to the power 3. So out of all these outcomes that we have, I have shown you this example, 4 outcomes: head, 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 tail, tail, head, tail, tail. Similarly, you can extend this to get all the possible outcomes, which are like 3, okay, 3 triplets. So you get this. So out of all the 8 possible outcomes, my desired outcome is 2, all heads or all tails. So what will be the probability? 2 by 8. So my P A intersection B, or A and B, is 1 by 4. Now for pairwise independence, it should be that P A intersection B, for what is the test of independence, should be P A into P B. So we have calculated P intersection B is 1 by 4. This is equal to half into half. We have calculated this. What was PA? PA was half and PB was half. So PA into PB, and you can see that these both sides are equal to 1 by 4. Hence A and B are we can say that pairwise independent. Okay. Now let's see if are they can they be independent? Are they mutually independent also? Not pairwise. Are they mutually independent? Let's just that also. How can they be if we check for mutual independence? So let's check for mutual independence. Check for mutual independence. What will be the check for mutual independence? Say for example, let's say that all the 3 tosses same thing. All 3 tosses are same. This is my thing. So what it should be? P A intersection B intersection C. Okay, so this should be again probability of head, 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 or tail, tail, tail. So as we have computed this earlier, you have seen this. This is equal to 1 by 4. Okay. But what is according to the definition of mutual independence, this should be equal to PA into PB into PC, right? So this side is 1 by 4, but this side is half into half into half. This is equal to 1 by 8. So we can see that this is not equal to 1 by 4 is not equal to 1 by 8. So we can say that A and B are not all, A, B and C. You can say for all. A, B, C are not mutually independent, but they are pairwise independent. Okay, I hope you get the point. So we have proven. So these are mutually independent. Sorry, these are pairwise independent, but they are not mutually independent. So this is our pairwise independence. Now let's go to the third one. This is the most important. It's after mutual independence. This is the base thing. Mutual independence is the base. This is the most important and widely used. This is second important. Okay. So this is conditional independence. So this comes from conditional probability. Okay. Similarly, conditional independence. So your independence is conditioned on some third event. Okay. Naturally, these two events means A and B cannot be may not be independent. But if you bring in a third event or a new information, then these two events become independent, and that is called conditional independent. How do we write it in words? So two events A and B are conditionally independent. Given a third event C if they are independent given that C has occurred. So what does this mean? That A and B are independent knowing that C has happened. So they are conditioned on C. Without that, they may not be independent. But if C has happened, then they are independent. So what do we know? That as in conditional independent, once we have a new information or new context, okay, then once C happens, so the new information changes the context. And now earlier A and B, which were not independent, now they have become independent. Okay, so we can write that occurrence of C brings in new information, okay, and changes the context, so that A and B become independent. Okay, so let me give you an example. So it's difficult to show you with an example because there will be a lot of maths. So I have brought an example which is intuitive to understand. It's more visual, okay, and intuitive to understand. It will give you the intuition that why it's happening. So let's see. So let me draw the same thing. Say for example, this is our sample space, the whole thing, say omega, and say this is having 50 events. Okay, this is 50, that's 50, and let's draw 3 events, A, B, sorry, let me draw bigger one, A, B, and then let's draw a C. So there are 3, A is there, B is there, and C is there. So this is bringing in new information, this third one. Okay, is bringing in the new information. So let me put some numbers in this set, so it's easier to visualize and see things. So for example, this is 4, this is 2, this is 1, this is 3, this is 4, this is 3, this is 12. We see that this is 50, our whole set contains 50. So what is the total sum? This is 3 plus 2, 5 plus 4, 9, 10, 13, 17, 12, 29. So the remaining of the space, this has 21 events. It's 21 count. Okay, so this is there. So now if you see what is the size of A, so A is equal to 4 plus 2 7, 8 3 11. This should be 10. Okay, 2 3 5 6 4 10. Two 1 2, no, 4 to 6 1 7 2 9. Sorry, this should be 3. This should be 3. Sorry for the maths. So this is 10, 4 plus 2, 6 plus 1 7 plus 3 plus 10. This should be 10. What is the value of B? B is 3 2 5 6 4 10. B is also 10. C is 12 4 16 17 3 20. So C is 20. Okay, and my omega is equal to 50. Okay, now let's compute all the probabilities. So what will be the probability of A? Should be equal to 10 out of 50. This is equal to 1 by 5. What is the probability of B? This is also again equal to 10 by 50. This is 1 by 5. Now what is P? A intersection B? A intersection B, what is A intersection B? This is A intersection B, right? So A intersection B is equal to 3 by 50. Now, is this equal to PA into PB? This is 1 by 5 into 1 by 5. is equal to 1 by 25. Definitely, if you see here, 3 by 50 is not equal to 1 by 25. This implies A and B are not mutually independent. Now let's see. Okay. Now we have got more information that C has happened. So as I mentioned earlier, that this becomes our world. So anything that is in this world of C, this is the new information. So our sample space comes down and this becomes our new sample space. So this is our samples because this has brought in new information. So what will be P? Now let's see. P of A given C. Okay, this is equal to P of A intersection C by P of C. What is A intersection C? Now let me see. P of B intersection C. Sorry. P of B given C is equal to P of B intersection C by P of C. Okay. Now let's see. What is P of, okay, what is P of A given C? P of C we know, we have seen here, P of C is 20. P of C is 20. Now what is P of A and C? A intersection C is and, right? A and C, this is 4, right? This is 314 from here. So this is equal to 4 by 20. Similarly, this C is 20, okay? And what is B intersection C? This is 5. This 4 plus 1 is 5. This is equal to 5 by 20. And what is P intersection? And what is A and B given C? What is P of A and B given C? This is our conditional mutual independence, right? P of A, P of B, and P of A and B. Everything is conditional on C. Let's compute this. So what will this be? This, if you consider this as one element, okay? If this, say for example, this is X and this is Y, then what will be this? This will become P of X intersection Y. So it will become X is A intersection B, intersection C. So this whole will become A intersection B intersection C by probability of C, right? This is equal to, I hope you get this, probability of A intersection B, if you consider this is X and this is Y, right? Then this will be our X and intersection Y. So this is our X intersection Y, or this whole thing. So what is probability of A intersection B intersection C? Let's see from the graph, from this, sorry, from the diagram. This is our part. This is the part A intersection B intersection C, common part in all. So this is equal to 1 by probability of C, we know 20. So now if you see, probability of A intersection B conditioned on C is equal to probability of A given on C into probability of B given on C. This is equal to 1 by 20 is equal to 4 by 20 into 5 by 20. 4 times 5. This is equal to 1 by 20. So both the sides are equal. And now you can, from here you can say that A and B are conditionally independent on given C has occurred, right? I hope you understood this. Okay, so this is there. So without this, without condition, if you saw that 3 by 50, this 3 by 50 was not equal to 1 by 20. But here if you see 1 by 20 is equal to 1 by 20. And because of C, this is independent conditionally, and without that, this is not independent. I hope the conditional independence is clear. Now let's do a quick summary of everything. Okay. Summary. Okay. So we understood, right? So we understood what is probability, what is events. Probability is the measure, numerical measure of the likelihood of any event happening. And events are, what are events? So let's go through them. I'll walk you through the notes itself. So the first thing was probability, event probability, numerical measure of likelihood. Then we saw event. This is an outcome or a set of outcomes of an experiment. When we do an experiment, like for example, toss a coin, we get head or tail. Okay, roll a die. We have seen this. We get, this is our sample space. Okay, so this is what we get. So this is an experiment we did. We rolled a die and we got this. So then we saw sample space. This is given, often denoted by omega. Okay. So sample spaces, it contains all possible outcomes of an experiment. This is a sample space. We have discussed about this too. Then I told you that we should know a sigma algebra. So the sample space should follow the rules of a sigma algebra. This is good to know. I'll put this content in the notes that we will have. Then we discussed about what is discrete and what is continuous. So in short, discrete, whatever is countable, or okay, if it is countable, okay, and that is finite, then it's discrete. And if it's infinite and if it's countable, then even then that is discrete. Else it is, if it is infinite and not countable, then we say that is a continuous. For example, when we have a graph like this, okay, or any line segment, okay, then this is what is discrete and continuous. And next thing that we discussed was what is mutually exclusive. Okay, that is disjoint. There is no intersection or overlap between the two events. So we can say that if we know one, the other has definitely happened. Then we saw independent events, means the two events, okay, the occurrence of one event has no impact on the occurrence of the other event. These two events are independent. For example, toss a coin twice. Then we discussed about what is the definition of, what is the meaning of probability of 0 and probability of 1. Okay, we discussed both of the cases. We say that why it's called highly unlikely, and why when probability of 0 is highly unlikely and probability of 1 is almost sure. Okay, and then we discussed conditional probability, where we understood that, okay, so if we have an existing probability and now we have got a new information, so on the basis of that new information we update the probability that we had already. So this is what is called conditional probability, and it's given by P, A given B, it's P, A and B by probability of B alone. Okay, then we saw this with an example, we understood this. The next was Bayes theorem. This is nothing but just a refactor of conditional probability to get it. And then I introduced you with to some terms, what is hypothesis, what is evidence, etc. Okay, and then posterior likelihood. These are good terms, this you should know. These are used widely in machine learning, that's why I introduced you to these terms. But these are nothing, just they have given these words, okay, so names to these terms, okay, that are used. And then we saw about, and then we discussed about total probability and a generalized Bayes theorem. Okay, so total probability, we saw that the whole sample space can be divided into A and A complement, and that can be generalized into n such parts, and the total probability of B can be found out by its intersection with all such parts. Okay, and this gave us the law of total probability, where we compute the any probability using its intersection with the mutually exclusive partitions of the sample space. This is our law of total probability, and the same law of total probability was used in Bayes theorem to replace the probability of B to get a generalized Bayes theorem. Okay, and after that we talked about independence of events, mutually exclusive, mutually independence, mutual independence, pairwise independence, and conditional independence. Mutual independence is our normal independence, okay, that we talked about earlier, okay, where PA intersection B is PA into PB. This is our mutual independence. And then we saw about pairwise independence, where we tossed the coin 3 times, and then we saw that how events were pairwise independent, where A was first and second toss are same. And here we computed what would be the then we found out that events were pairwise independent but not mutually independent. Similarly, and the third and the most important part was conditional independence, where we saw that event, okay, 2 events A and B are independent given on some condition or some new information that we have. Okay, this we understood using this diagram of the sample space and 3 sets. Okay, and here we computed that without the condition A and B were not mutually independent, but based on the condition given that C's information, we found out that A and B were conditionally independent. That's all. So that's all we have for this video. Thanks for watching this video. Have a good day and see you again in the next video. Bye for now.